In the deep ocean, the most important thing is not what you can see, it's what you can hear. Last time we followed sonar as a way of seeing with sound. But today we face a problem that every sonar operator eventually learns the hard way. The ocean lies. Two ships can use the same sonar in the same region on the same day, and one will hear a target clearly while the other hears nothing at all. Not because the target is silent, but because the water is shaped like a lens. To understand modern undersea stealth, you don't start with submarines. You start with physics. Because the ocean is not one big tank of water. It's layered, sometimes neatly, sometimes violently, and those layers control how sound moves. And when sound moves differently, the ocean creates hiding places that don't exist on any map. Here's the core idea. Sound doesn't travel through seawater at one constant speed. Its speed changes with temperature, pressure, and salinity. And when sound speed changes with depth, sound doesn't go straight, it bends. That bending can carry sonar energy away from you, or bring it back to you, or skip right over a target like it was never there. A sound speed profile is basically a vertical scan of the ocean. How fast does sound move at each depth? Example: if the surface is warm, sound travels faster near the top and slower below where water is colder. Now we introduce a layer that matters more than almost anything else in submarine detection. A thermocline is a zone where temperature drops fast with depth. Example: a submarine above the thermocline may be heard clearly by surface sonar, but the same submarine below it can sound like it vanished. That bending is called refraction. Example: when sound enters slower water, it bends toward that slower region, like light bending through a lens. And in the ocean, that lens can be enormous, hundreds of meters thick, stretching for kilometers. So what does this do to sonar? Imagine a ship using active sonar. It sends out a pulse, maybe a ping, and listens for the echo. But the ping doesn't radiate evenly into infinity. It gets sculpted by the water. Some angles bend downward into the deep, some curve upward and hit the surface and scatter. Some get trapped in a layer and travel far beyond what you'd expect. And the most dangerous result is this. The ocean can create a region where sonar simply can't reach. A shadow zone is exactly what it sounds like, a blind spot made of physics. Example: a sonar pulse can bend downward, then upward, leaving a band of water in between with almost no sound energy. If a submarine sits inside that band, it may be dramatically harder to detect. Not invincible, but hidden, the way a mountain can hide a town from radar. This is why depth matters. People think submarines hide by being quiet. They do. But they also hide by choosing where the ocean itself will protect them. Sometimes that means sliding just below a thermocline. Sometimes it means going deeper into colder water. Sometimes it means doing the opposite, staying shallow when the surface layer forms a duct. Let's talk about that. A surface duct happens when sound speed conditions near the surface cause sound to curve back downward, then upward again, trapping it in a shallow band. Example: in a strong surface duct, sonar from a ship can travel unusually far near the surface, but may struggle to look beneath the duct into deeper water. So the same ocean can help you, or betray you, depending on where you are and where you're trying to listen. And here's where it gets interesting. These layers are not constant. They shift with seasons. They shift with storms. They shift with currents and river outflow and sunlight. In some places, the thermocline is strong and sharp, like a wall. In others, it's weak, messy, broken into multiple layers. A sonar operator is not just hunting a submarine. They're hunting through a living, moving medium. That's why navies measure the water. They drop sensors to record temperature and salinity versus depth. They build a sound speed profile. And they feed that profile into models that predict how sonar energy will bend. Because if you don't know the ocean's layers, you're fighting blind. Now we reach one of the strangest features in underwater acoustics. A place where sound can travel farther than almost anywhere else in the sea. The SOFAR channel, short for sound fixing and ranging, is a deep zone where sound speed reaches a minimum. Example: because sound tends to bend towards slower regions, sound rays get guided into this channel and can propagate over huge distances with low loss. This is not a submarine trick, it's an ocean feature, and it means the deep sea sometimes acts like a waveguide, a natural tunnel for sound. But there's a paradox here. If sound can travel far in the SOFAR channel, that can help detection, because distant sounds may reach you. But it can also spread noise, shipping noise, storms, distant machinery, making the background more crowded. And this brings us to a concept sonar crews care about. Where does sound return strongly, and where does it fade out? A convergence zone is a region where refracted sound paths bend and refocus, creating a ring of higher intensity at a certain distance. Example: a target might be weak at 20 kilometers, then surprisingly stronger at 50 kilometers, because the sound refocused there. This is why detection range is not always monotonic. It doesn't always fade smoothly with distance. Sometimes it fades, then comes back. Now, put yourself inside a submarine for a moment. You are not only thinking, "Am I quiet?" You are thinking, "Where is the ocean loud? Where is it blind?" You ask questions like, "Is there a strong thermocline today? Is there a surface duct? Where are the shadow zones likely to be? What depth gives me the best chance that active sonar energy will bend away from me?" This is why submarines change depth like a chess move, not randomly, strategically. And this is also why anti-submarine forces use multiple tools. If one sonar path is blocked by a shadow zone, they might change the depth of the sonar source, drop sonobuoys at different depths, use passive listening from multiple positions, or reposition the ship to exploit a convergence zone. The ocean is a three-dimensional puzzle. Here's the key takeaway. The most important terrain in undersea warfare is invisible. It's not mountains and valleys. It's not borders. It's the shape of the ocean's layers, the way temperature and pressure sculpt the path of sound. And that terrain can change in hours. So when someone says, "Just use sonar," the real answer is, sonar is not a flashlight. It's a beam traveling through a moving lens. And a lens can create blind spots. Somewhere below, a submarine slides along a boundary you cannot see. Above it, the water is warm, fast for sound. Below it, the water is cold, slow for sound. Between them, the ocean bends acoustic energy like glass. A ship could be shouting into the sea, and the sea could be whispering back, "Not here, not today." In the next episode, we'll take this one step further, because knowing the layers is not enough. Real sonar operators have to search through them, in real time, with imperfect information, while the ocean changes under their feet. Silent Oceans continues.